Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 14.2, day 1, entitled Probability. And we're going to talk about all these different objectives over the next couple of days, and we're going to talk about a little bit of both of them each day. So we'll talk about probability, calculating probability, the complement of an event, which is really a shortcut for helping us find a certain probability. And then we'll talk about unions and intersections, which we talked about way back in chapter 1. And then we'll talk about conditional probability as well. So first, let's define probability. Okay, when we're discussing probability, we're going to define some terms, such as an experiment, and that's just a process that you're doing. It could be tossing a coin, it could be choosing a card from a deck of cards, it could be rolling a die. So it's whatever event you are testing. And then the results that you get are going to be called the outcomes. So we have experiments and we have outcomes. And then the sample space of an experiment is the set of all the possible outcomes. So if you flip a coin, you have a choice between heads or tails. That's your sample space. So the first few problems that we're going to be working with are just getting familiar with that sample space. And this table gives you a good overview of some of the very common sample spaces that are used in statistics. And some of these you might be more familiar with than others. Hopefully you know that when you're tossing a coin, you have options of heads or tails. If you're rolling a die is just called what you call one dice. Dice is technically plural. There's 2 dice or 3 dice. But just one of them is called a die. And we're going to assume that it's a standard 6-sided die. If it's not, then they'll tell you how many sides it has, because you can have a 20-sided die, for example. Here they have tossing a coin twice. So you could have heads, 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 tails, tails, heads, or tails, tails. Picking a card from a deck. Sometimes students aren't as familiar with a deck of cards. So if you have any questions about the terminology for a deck of cards, definitely ask. There's 4 suits. We've got hearts and diamonds and then clubs and spades. And there's kings and queens and jacks. And then there's the numbers 2 through 10. And then there's aces. And sometimes aces are thought to be like a number 1. Sometimes they're thought to be higher than a king. So it kind of depends on the situation. But definitely ask if you need any clarification on what is in a deck of cards, a standard deck of cards. And then here, this is just another example where we've got patients that are recovering or not recovering after a certain treatment. Okay. So this is just the way that you can write your sample space is with those curly brackets, and then you list all of the possible outcomes. Now, when we were dealing with tree diagrams, we came up with all of the possible outcomes for our sample space as well. We just counted how many there were. Now they're going to want us to list them out for some of our examples. So if we look at this next example, it says 2 dice are rolled. Write the sample space. Now, this one we'll probably go through in a little bit more detail in class, but this one can be kind of tedious because if you roll the first die and get a 1, then the second one could also be a 1, or it could be a 2, or it could be a 3, or a 4, or a 5, or a 6. And then your next die that you roll could be a 2, the first one could be a 2, and then the second one could be a 1, or a 2, or a 3, or a 4, and so on and so on and so on. And you'd have to do that for 3, 4, 5, and 6. You'd have to list all the pairs. Okay, so when you get done, you would have the whole list of 3s with 1 through 6, the whole list of 4s with 1 through 6, the whole list of 5s with 1 through 6, and the whole list of 6 with 1 through 6. So there should be 36 of them altogether. Okay. So that would be your entire sample space. You would have to list out all the pairs. So that's kind of tedious. but that's what we would have to do. And just to save time, I'm not going to write them all out. But if you have questions, we'll go over it in class. Okay? And then when you're tossing a coin 3 times, this is a little bit better to actually draw out. And this is where a tree diagram could be helpful. If you toss the first, or you do the first flip, you could get heads or you could get tails. And then for your second one, again, you could get heads or tails. And then for your third one, you could get heads or tails. So here again, if you do tails, the next one could be heads or tails. And then each of those could be heads or tails. So this one's small enough that we can draw the little tree diagram, or if we wanted to list everything out, we would just follow each of these little branches. So we could have heads, 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 or we could have heads, heads, tails. Then we could have heads, tails, heads, or we could have head, tail, tail. And then we could do the same down here. Okay, so when we get done, we'll have 8 all together. So tails, heads, heads, tails, heads, tails, 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 heads, and then tails, tails, tails. Okay, so that's not a huge sample space to worry about writing out. There we have 8 different options. 1, 2, 3, 4, 5, 6, 7, 8. And the tree diagram really helps us count those as well. So if you want to think of it in terms of a tree diagram, or if you want to go ahead and list, either way of thinking through it is correct, but your book is going to want you to list out all the options and then write it in the curly brackets with your sample space. So we need to make our answer look like this with the curly brackets and then the commas in between each option. So technically just making a list like this isn't correct. We'd have to do the little curly brackets and then comma, 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 comma all the way through, and then curly brackets at the end. Okay? So when you check the answers in the back of the book, that's what it's going to look like. All right, but I'm sure we're pretty good with understanding that concept of what the sample space is. And when we're dealing with our experiments, we're going to be concerned with the experiments for which all the outcomes are equally likely. That's one of the big fundamental concepts of statistics, is that everything is equally likely to happen. Okay, so when we toss a coin, we're going to assume that it's perfectly balanced. It's not weighted heavier on heads or tails. Same thing for a die. When we roll a die, we're going to assume that it's a standard weighted die. It's not weighted inappropriately so that it rolls a 6 more often. Okay, so we want everything to have an equally likely outcome. Okay, so that way if the experiment is repeated over and over, we can expect about the same results every time. And this is key in science as well. When you have big medical studies that are done, you want to make sure that it can be repeated, and if somebody repeats it, they can get close to the same results. So for mathematics here, if S is the sample space of an experiment, then an event E is the subset of the sample space. And there again, it's going to be all those equally likely outcomes. Okay, so let's take a look here at this example and let's just think through how many different events are going to be in these sample spaces. And this refers back to the coins that we listed earlier. So I'll be flip-flopping back and forth between the screens. But here, an experiment consists of tossing a coin 3 times and recording the results in order. List the outcomes in the sample space and then list the outcomes in each event. So we already listed the sample space. That was right here in part B. That's why I took time to actually list these out, because we'll need these to do this first example. Now, if you didn't have them already listed, then you'd have to take time and actually list them out. But we've already done that. So now we can find the sample space and then list the outcome of each event. So an event of getting 2 heads, exactly 2 heads. So I'm going to go back and I'm going to look at my list here. I've got 1, 2, 3, of getting exactly 2 heads. And I see 4. But for some reason, I feel like we're supposed to get 3. Okay, and I figured out why we're only supposed to have 3. That's because I wrote this one incorrectly. So here this should be tails, tails, heads. Okay, so now the ones that have exactly 2 heads are going to be right here, and right there. So I have 3 out of 8. So 3 out of the 8 events are going to have exactly 2 heads. And then to list them, I would write heads, heads, tails, heads, tail, head, or tails, head, head. Okay, and if we look at part B, we want to find the event of getting at least 2 heads. So now if I go back, that means I could have 2 or more. I could have 3. So here's 3. All 3 of them are heads. There's 2, there's 2. So that's 3 so far. There's another 2, and the rest of them have 1 or none. So now there's going to be 4. So I have 4 out of 8. So that would reduce down to 1/2, of course. So that would be my probability. And then listing all of them, I would write heads, 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 and then the same 3 that I had before. Heads, heads, tails, heads, tails, heads, and then tails, heads, heads. Okay, last one is the event of getting no heads. So I'm going to go back, and if I don't flip any heads on the coins, then that means I'm going to have all tails. And there's only one here that has tails, tails, tails. So that then would have a probability of 1 out of 8. And my event then would be tails, tails, tails. Okay, so we're listing the outcomes in the sample space and then listing the outcome in each event. All right, so now we're going to move on to our actual definition of probability. Okay, and this you've kind of noticed in that last example, it was the things that we wanted. So if you want no heads, that means you want all tails. So we had 1 event that we wanted out of the 8 possible. So here our definition is going to say, let S be the sample space of an experiment in which all outcomes are equally likely, like we've talked about before, and let E be an event. Then the probability of E is written as this, P of E. So N of E is going to be the number of elements, and N of S is going to be the number of elements, but this is in E, our event, and then this is S, our sample space. Okay, so another way to write this in a little more understandable terms is to say that this is going to be the event that you want over your set, your sample space. Or I like it even better just saying it's what you want to get out of the total options that you have. That's a much more user-friendly way of thinking about it, okay? But no, just know that this P of E is how we're going to write it mathematically, the probability of some event. Now, since we're dealing with fractions here, we could have our the number of our events and the number in our set go anywhere from 0 to that maximum number that's in our set because it's less than or equal to here. So I could have nothing in my elements, and then I could get all of the elements of the set. So my probability, my answers for my probability can really go anywhere from 0 to 1. So it could be any fraction or decimal between 0 and 1. And a way to think of that is kind of like a number line. Okay, and I'm going to kind of draw it as more like a big line segment. So down here we'd have 0, And then at the other end, we have 1. Now, the closer you are to 0, that means the less likely it's going to happen. And if something has a probability of 0, that means that it's impossible. It's not going to happen. And then if your probability is 1 or close to 1, that means it's very likely to happen. And if it's equal to 1, that means that it's certainly going to happen. It will definitely happen. Okay. And then 0.5, that would be, you know, your 50-50 chance. You have an equal chance of getting either. And then you'd have, you know, 0.75 in here and 0.25 here. So 0.25, that's kind of, you know, unlikely, not really going to happen, but it could. 0.75 is a little more likely. It's likely to happen. And you hear about this a lot, like when you're dealing with weather. There's a 60% chance of rain. Okay, 60% would be right about in here. So it could happen. It's probably going to happen. If you say that there's a 10% chance of rain, oh, that's pretty small, so it's probably not going to rain. Okay, so that terminology I know you're pretty familiar with because it's real world, it's user friendly. So then let's talk about this here. Let's go back to that coin tossing, and here we're going to find the probability of the following events. And these are the same events that we dealt with before when we wanted to get exactly 2 heads when we flipped our 3 coins. And we wrote that down before, actually. We had a probability of 3 out of 8. And then the event of getting at least 2 heads, that's where we had 4 out of 8. And we reduced that down to 1/2. And in the event of getting no heads, that's where we had all tails, so there was 1 out of 8. So those are the fractions that I wrote down here. These are our probabilities. And I was just trying to get you to see that there are 3 options that we want out of the total 8, and then we list 3. And there were 4 out of the 8, so we list 4. And there's 1 out of the 8, so we list 1. Okay? So listing those outcomes helps you count what you want, and then you make it that part your numerator of the fraction. And then numerator is what you want, and denominator is all the possible events. Okay, so listing out your sample space gives you all of your events. Looking for a specific number of events and listing them out, that gives you what you want. And if you make it a fraction, then you have your probability. Okay, so now we're going to talk about how we actually calculate probability by counting. And to find the probability of an event, we do not need to list all of the elements. Thank goodness, because that was really tedious in that opening one where we were supposed to list all 36 combinations of rolling 2 dice. So what we need is the number of elements. So we don't have to list everything out every time, we just need that number. Okay, so how we can count those numbers then is like this with our combinations. Here we have a 5-card poker hand is drawn from a standard deck of 52 cards. Now, poker is just one of those examples that gets used a lot in statistics, so I'm not an expert on that game by any means, so you don't need to be an expert in it in order to do this calculation here. But if you have questions about it, we can obviously talk about it in class. So what is the probability that all 5 cards are spades? Okay. So when we're dealing with this situation, we have to think of the number of elements that we have. Now, we're dealing with 52 possible cards, and we're just drawing 5 of them. Okay? And order doesn't really matter here because as long as you have the same 5 cards all together in your hand, it doesn't really matter which one comes first. So this isn't going to be a permutation, this is going to be a combination. So we want 52 cards and we want to choose a combination of 5. Okay, so when you calculate that out, you get 2,598,960. Wow, that's a lot. Now, the ones that we actually want to draw are going to be spades. Okay, now in a deck of cards, there's 4 suits. And there's the same number of each suit. So you're going to take 52 and divide it by 4, and you actually get 13. So there's 13 hearts, 13 diamonds, 13 clubs, 13 spades. Okay, so of all of the spades, of all 13, we want to choose 5 of them. And again, it doesn't matter what ones they are, so order doesn't matter. We can just do a combination here. Okay, so then when we calculate that, we'll get 1287. And remember, your calculator can do these combinations for you. But now this is what I want. This is all 5 spades, and this is my total my total set. Okay, so then to actually write out my probability, I would put the 1287 over the 2,598,960. Okay, so that's the probability of my event happening. Now you can reduce that down if you want. You can make it a decimal. It's 0.000495. So that is pretty darn close to 0. So the chances of that happening are pretty slim. Okay? Okay, so let's move on here then, and let's talk about the complement of an event. And this is where you have an easier shortcut way to do the calculation, because sometimes finding a specific event is really, really challenging, but if you find the opposite of it, that's really easy. So the complement basically is the complement of an event is the set of outcomes in the sample space that is not in the event. So we're going to call that E prime with a little markup above. Okay? And how we find it is we take 1, the 100% chance, minus the probability of our certain event. And then we'll get our complement. And we can do this the other way too. We can take 1 minus our complement, and that can give us the probability of an event happening. So that's kind of the shortcut that we're going to be using. Okay, so let's take a look at a situation here then. We have a basket that contains 10 red balls and 15 yellow balls. So altogether there's 35. 6 of the balls are drawn at random from the basket. What's the probability that at least 1 is red? Now the key phrase here is that it's at least 1. So that means we could have 1 of them, or 2 of them, or 3 of them, or 4 of them, or 5 of them, or 6 of them. That could all be red. So I don't want to find 6 different numbers and then combine them all together. So the easier way is to find the complement of that. So this is our event. This is what we're trying to find. So my complement then, E prime, that would be where if at least 1 is red, or 2 or 3 or 4 or 5 or 6, so 6 would be all of them are red, then the opposite of that would be where none of them are red, where they're all yellow. So if I can find that, that's going to be the easier option, the easier calculation. Okay. So here I have 15 that are yellow, and I want to choose 6, and I want them all to be yellow. So if I'm going to calculate my total of them being yellow, or my chances of them all being yellow when I draw, I'm going to have 15 that I'm choosing from, and I'm going to want all of them, all 6 of them, to be yellow. And again, this is a combination. It's not a permutation, because it doesn't matter what order I put them in. They're just yellow, yellow, yellow. Okay? So that will be 5,005. Now I still need my total. Okay? And my total then, I've got 25 altogether, the 10 and the 15, I have 25 altogether, and I want to choose 6 of them. So I'm going to have 177,100. Now, if I put that together in a fraction and reduce that down, I'll get 13 out of 460. Okay? So that is my um, P of E prime. That's my complement. So now I still have to find the probability that at least one is red. So my P of E, I'm going to have to take 1 and subtract my complement, 13 out of 460. So then when I subtract those, I'll get 447 out of 460, or a 0.972. So either way you want to write it, as a fraction or a decimal, doesn't matter. Okay, so now let's talk about unions and what it means to be a union. Now we've talked about unions way back in chapter 1 at the start of first semester, and this is where you have like everything from your room and everything from your siblings' room, and you put it all together, okay? But statistically, we have to think of it a little bit different when we're doing our calculations here, okay? So this is where we're dealing with a type of an overlapping event, okay? Overlapping. Because sometimes you can have the probability of um, one event, like the probability of speaking French and the probability of speaking German, but then you have to subtract out all the people who can speak French and German, okay? So remember this union here, this little U is for union, so that's like an OR. And this one here for the upside down U, that little N, remember that's for an intersection. Okay, so this means and. This is the stuff that's in both of them. It's in E and F. Okay, so let's take a look here. What's the probability that a card drawn at random from a standard 52 card deck is either a face card or a spade? Okay, so when we're dealing with this situation, we want to deal with how many face cards we have. Now there's kings and queens and jacks. So there's 3 of each. There's a king and a queen and a jack. And then there's 4 suits. So there's going to be 12 face cards altogether. Okay, so there's going to be 12 out of the 52 that are face cards. Okay, and then for spades, that's one of our suits. And I said there's 13 of those, so that's 13 out of 52. However, when I count my face cards and I count my spades, I'm also counting some of my face cards that are spades. So I have to subtract off that overlap. So there's going to be a king and a queen and a jack that are the spade face cards. So I have to get rid of those 3. So then when I add and subtract there, I'll get 22 out of 52, and that's going to reduce down to 11 over 26. So again, this is what I want over my total. And I just have to make sure here that I'm counting one and counting the other, and then I'm subtracting the overlap. So this is my intersection here. Okay, that's our intersection. So that's the face cards that are spades. Okay. All right, so then we have to also talk about mutually exclusive events. So this is when things don't overlap. So this is where you have an intersection of 0. So E is completely separate from F. So here we're just going to deal with this event or this event. Okay, so this is our union. You've got this or this happening, and you add them together. Okay, so here we can think of this as mutually exclusive. Mutually exclusive. So this would be like people who have cats and people who have dogs, not people who have cats or dogs. Okay. Better example though is here. What's the probability that a card drawn at random from a standard 52 card deck is either a 7 or a face card? These are separate events because there's no way that a 7 can be a face card. Okay, a 7 isn't going to be a king or a queen or a jack. A 7 is just a 7. Okay, so they're not going to overlap at all. But you have to know how many of each you have. So there's one of each number, 1 through 10, or ace through 10, but there's one of those for each of the sets, or each of the suits. So there's going to be 4 out of 52 that are 7s. And then I have to know how many face cards there are, and that's like what we just calculated. There's a king, queen, and a jack, that's a J, for every suit. So 3 times 4 would be 12 out of 52. So that's how many of our face cards we have. And then here, since we don't have any that overlap, the 7s aren't going to be the face cards, we can just add those together. 16 out of 52. And then we can reduce it to 4 out of 13. Okay? So there is a difference between the overlapping and the exclusive events. So when you read these problems, just take a moment and think, do these have anything in common? Okay. All right, one last concept we have to talk about then is our conditional probability. And conditional probability is just how we narrow our possible outcomes for our denominator in our fraction for our probability. And it all deals with a specific phrase. It deals with given. So the probability of an event given that another event has occurred is written this way. The probability of E happening given F. So here they have an example. Let E be an event of getting a 2, and then F be the event of getting an even number if you're rolling a die. Okay? So if you say, I want to find the probability of E given F, that's what this little line means. This little line means given, okay? So if I want to find E given F, that means I want to find the number is 2, given that the number is even. So you're finding the probability of getting a 2 out of those even numbers. So instead of dealing with all 6, you're just dealing with a smaller set. Okay, so again, here we have our Venn diagram with the 2's and then the evens, and then this would be the overlap. This is where the 2 is an even number. So we would end up with one of the 2's out of the 3 even numbers, so we would get 1/3 for our probability. Okay, so the way we calculate this then is with this little equation right here. And this is just the number of E and F. So remember, again, this is your intersection. That's where you think and. It has to be both E and F over just the number that's in F. Okay. So this last example is a little tricky. Here we're dealing with a mathematics class that has 30 students, but 12 of them study French, 8 study German, and 3 study both of these languages. And the rest don't study anything at all. No foreign language at all. So we want to draw a Venn diagram of this situation. So you know what a Venn diagram is. It's where you have the overlapping bubbles. We've seen all kinds of them, okay? So our whole set here, this is going to be our class of 30, okay? And we're going to have some that speak French, and we're going to have some that speak German, and then here is going to be the overlap where there's both, okay? Now, all together in my whole French group, there's going to be 12 of them, but there's 3 that know both, okay? So I'm going to put the 3 in here, and then 12 minus 3 is 9. So there's 9 that study just French, but if I do 9 and 3, that gets me the 12. And then the same thing for the German. I've got 8 that study German, but 3 that study both. So then there's 5 that study just the German. Okay? So then really the 9 plus the 5, that gets me 14. And then I have to worry about how, 14 plus these 3 is going to be 17. So there's 17 altogether that are speaking some form of foreign language. Okay, the 9 plus 5 plus 3, that gets me the 17. So that means there's 13 that are outside of that group that don't speak anything at all. Okay, no foreign language at all. So that's similar to the picture that they have drawn here. Okay, so then we're going to answer a couple questions about that, and we'll refer back to our Venn diagram if we need to. So if a student is chosen at random, find the probability that each of the following occurs. The student studies French. Okay, so there are 9 that study just French, and there are 3 that study German and French. So that gets us our total 12 out of 30. And you could think of that as the 9 and the 3 separate, or this whole circle gets you the 12. Okay? And then 12 out of 30, we would reduce that down to 2/5. So 2 out of every 5 students studies French. Okay? And then the student studies French, given that he or she studies German. Okay? So this is that whole given. Okay? So out of the ones that study German, if we look again, here's all the ones that study German. The ones that study French, there's only 3 of those whole 8. Okay? So there I'm going to have 3 out of 8. And I can't reduce that down anymore. Okay? So watch out for that phrase, given. And then part C, the student studies French, given that he or she studies a foreign language. So this is just the students that study French. So that means all of the French, so that's 12, out of all of the ones that study a foreign language. So that was 17 altogether. Okay? And again, we can't reduce that down anymore. Always reduce your fractions if you can. Okay? So I know there's a lot of information in this section. It's a lot of little details, but it's all very similar. It's just dealing with knowing what you want out of the total and making sure that you either include certain groups, or maybe you need to subtract off the extra overlapping ones. So read the problems carefully, watch out for that key vocabulary like given, and definitely take a look at the odd problems in the back of the book. And if you have questions, come on in and see me before school.